Hello and welcome back. In 3.4 we get to work with the chain rule. Also arguably called the composition rule. So a little mini review on composition of functions. If f of x is, let's say, x squared and g of x is, let's do e to the 3x. F of g of x, which can also be written as you see there. It says keep the framework for f. All of your x's are now g of x's, though. So framework of x is something squared, and plug in g of x. Then simplify where possible. So this would be e to the 6x. And just a little reminder that composition is not a commutative operation. G of f of x says keep the framework of function g and plug in function f. So g of f of x be e to the 3x squared, not equal to e to the 6x. So the order does matter on these. Now they have us kind of work backwards in this one. We look at the special case first, and then we see the general chain rule itself. So the special case here would be the general power rule. So that one we can sort of demonstrate how it comes about. So let's say that f of x is some function g of x squared. Well, squaring means multiplying two copies of something together. And as you'll recall from the previous section, using the product rule, we would differentiate the first, keep the second, plus then keep the first, differentiate the second. But notice multiplication is commutative, so we just have two of the same thing. So f prime of x is two of these g of x times g prime of x's. Let's build on that. So now let's expand this out to f of x being g of x quantity cubed. So again, I'm going to set it up as a multiplication, since we know the product rule. So f prime of x, derivative of the first, which we saw on the previous line, was 2g of x g prime of x, times keep the second, plus then keep the first, differentiate the second. So notice on this term we do have g of x times g of x, which is g of x squared. So f prime of x, we have 2g of x squared times g prime of x plus 1 of the g of x quantity squared, g prime of x. So we have 3 of those. So I'm going to ask you to try out f of x is g of x to the 4th. See if you can figure out what the derivative would look like for that. Go ahead and pause it, come back when you're done. Welcome back. There's a few different ways to do it. I'll just use g of x squared times g of x squared. You might have used third power and first power. That's fine too. So an f prime of x by product rule, derivative of the first factor, which we saw was 2g of x g prime of x, times keep the second factor, plus then we trade roles, but these will be the same again, since each factor is a g of x squared. So g of x times g of x squared is g of x cubed. So we have 2 g of x quantity cubed, g prime of x, plus 2 g of x quantity cubed, g prime of x, and then just hit our like terms there. So we have 2 and 2 of those. We've got 4 of these. G of x quantity cubed, g prime of x. So hopefully you're noticing a pattern emerging that these do look like the basic power rule that we had before, where the exponent becomes a factor. We keep the base, we drop 1 off the exponent. The only big difference is we have to remember to multiply by whatever g prime of x is. But otherwise, this looks like the power rule that we looked at before. So it's sort of the general format for the general power rule. If we have f of x is g of x quantity to the n, then f prime of x is n times g of x to the n minus 1 times g prime of x. Okay, so where that comes in handy, let's say we had f of x was 5x plus 2 quantity raised to the 10th power. A little bit more time consuming to write out 10 copies of the binomial, even with the little trick we can use with the binomial expansion using the Pascal's triangle. It would still take a little bit of work to get there. This one we can use the general power rule to differentiate. F prime of x, I would hang on to the 10 as now a factor, keep the base, drop 1 off of my exponent. The most forgotten part, if you keep forgetting it, write it in red ink, blue ink, write it in something that'll stand out until you remember to write it. We also have to multiply by the derivative of what's inside here. The derivative of 5x plus 2 is 5. So then f prime of x would be 50 times 5x plus 2 quantity raised to the 9th power. If we have g of x is x to the 4th plus 2 quantity raised to the 5th, g prime of x, then the exponent becomes a factor. Hang on to your base, drop 1 off your exponent. That part you should hopefully have almost automatic at this point. The only new part, remember to differentiate the inside. So derivative of x to the 4th plus 2 would be 4x cubed, and then just do a little bit of cleanup, a little simplifying. So 20x cubed by x to the 4th plus 2 quantity to the 4th. Let's see, we'll do one where we have to do a little bit of legwork at the beginning. So this one is not ready to be differentiated yet. we'll rewrite this with a negative exponent. Now we're in the right format of our function is some other function raised to a power. Now we can use the general power rule. So p prime of x, -4, is now a factor. Hang on to the base. Decrease the exponent by 1. Watch your sign work there. -4 minus 1 is -5. And multiply by the derivative of the inside. Derivative of x squared is 2x. Derivative of a plus 2x is plus 2. Derivative of a constant is 0. It drops off. So p prime of x, we can go ahead and multiply the -4 with this stuff since it's only raised to the fourth, or raised to the first. This one raised to the -5th, I cannot distribute here. So we'd have -8x minus 8 over x squared plus 2x plus 6 quantity raised to the 5th power. So I'm going to give you all one to try out. So we'll do r of x, cube root of x squared plus 1. So go ahead and differentiate that. Okay, welcome back. So first step, we keep it as r of x. So we're not ready to differentiate yet. We have to write it in a different format. Cube root is the same as the 1/3 power. Again, this is r of x, not r prime of x yet. Now we're ready to apply that general power rule. So r prime of x, the 1/3 that was an exponent, is now a factor. Hang on to the base. Subtract 1 from the exponent. So 1 I'll think of here as 3/3. 1/3 minus 3/3 is -2/3. Multiply by the derivative of x squared plus 1, which is a 2x. So r prime of x would be 2/3 x by x squared plus 1 to the -2/3 power. And there's a few different ways they could write that. They might write it with or without the negative exponent. So you may see it as r prime of x, 2x over 3 cube root of x squared plus 1 quantity squared. Same thing. These two are the same. So that's our general power rule, which is just a special case of the chain rule. So let's take a look at the chain rule. Can also be thought of as the composition rule. So we'll let m of x equal f of g of x. Well, then m prime of x would be the limit as h goes to 0 of f of g of x plus h minus f of g of x all over h. Now, what we're going to do from here is we're going to use that idea again of multiplying by 1. We're going to multiply top and bottom by the same value. So m prime of x, I'll keep what I had before. The limit as h goes to 0 of f of g of the quantity x plus h minus f of g of x all over h. And we're going to multiply top and bottom by the same thing. We're going to multiply top and bottom by g of x plus h minus g of x over the same thing, g of x plus h minus g of x. So we've multiplied by 1. the next thing we're going to do here is switch our denominators. And the reason we're allowed to do that, recall, if we have a over b times c over d, we get the same value as if we had a over d times c over b. Multiplication is commutative, so we are allowed to switch denominators like that. So m prime of x is the limit as h goes to 0. I'll keep that first one as it was, first numerator as it was. But I'll flip this denominator to the second denominator. Second numerator stays as is, the denominator flips around. So then taking care of those, m prime of x is now f prime of g of x times g prime of x. So this one we basically had the same setup of f of x plus h minus f of x over h, only instead of an x plus h we have a g of x plus h and a g of x. Our second one, though, this is clearly recognizable as just g prime, g of x plus h minus g of x over h. Now, another option available to us is to use the idea of the other notation dy over dx. And we can sort of make simpler differentials and solve that way. That's another option available to us. I find students have an easier time following this version of the chain rule, but both of these are the chain rule. It looks odd, but they're really two versions of the same idea. So for example, if y is u to the 1/2 and u is 5x squared plus 8, 8. We'll go with 8. Doesn't matter. Then dy du 1/2 times u to the negative 1/2, so subtracting 1 in the form of 2/2 here. Du dx, derivative of u, treating x as the variable, 5 times 2x to the first, derivative of a constant drops off. So then dy dx would be dy du times du dx. So dy du 1/2 u to the negative 1/2 times du dx would be times 10x. And then a little bit of simplifying. So 1/2 by 10 is 5, so we have 5x. Instead of u to the negative 1/2, u we know is 5x squared plus 8, then to the negative 1/2 power. It is possible that your author, or more likely your author's graduate assistant, will take one more step and drop that into the denominator with a positive 1/2, or even drop it underneath a square root in the denominator. Those are fine as well. So let's to one where we have to find our own substitutions. So we're going to find dy dx given y equals e to the 10 plus natural log of x quantity squared. So not natural log of the value x squared. Just a little reminder. So our goal is basically to write something that's easier to differentiate each time. So instead of y equals e to a big mess, it would be easier to differentiate if it were e to just one thing, the u. So then we do that by saying let u equal this ugly mess up here. So now we have something that's easy to differentiate here. We have something that's easy to differentiate here relatively. I don't know, it's not simple. We're in calculus. It's not easy. I'm saying it's less challenging than other ways of doing it. So I want two things. I want to find dy du. Derivative of e to the u is still e to the u. I'll also find du dx. Derivative of a constant is always 0, and here we're using our general power rule. So I would make that exponent into a factor. I would hang on to the base, subtract 1 from the exponent, and then don't forget multiply by the derivative of the argument. Derivative of natural log of x, remember, is 1 over x. We saw that in an earlier section. So dy dx will just be the product of those. So e to the u times 2 natural log of x over x. And then the only other thing we have to do is get it back to the original. We want dy dx. We don't want u involved. So u we will back substitute and get rid of it. So dy dx is e to the 10 plus natural log of x quantity squared times 2 natural log of x over x. And that's as far as we go with simplifying that one. Now it's written it all in terms of x's and y's. So again, just picking out the u, it does take a little practice to pick out what the easiest u would be for the problem. Sometimes we will have to do a couple of iterations, a couple of substitutions, but generally this is the idea that we'll use with these. So let me have you all try one out. This is one of your authors. So you're going to find dy dx or y equals natural log of 1 plus e to the x quantity cubed. So you may need a couple of substitutions. So go ahead and pause, give it a spin, and unpause when you're done. Okay, welcome back. So first thing I see is that if this were y equals something cubed and just a basic something cubed, it would be easier to work with. So that's what I'll turn it into. So I'm going to say y is u cubed, which means that we let u equal that stuff inside, natural log of 1 plus e to the x. Now here's where we need one more substitution though. We know how to differentiate natural log of x. We don't know how yet to differentiate natural log of another argument unless we use this substitution again or the chain rule. So we're going to let w equal 1 plus e to the x. So now we have y equals u cubed. U will now equal natural log of w of just one thing, and w is 1 plus e to the x. So I'm going to differentiate each one of these. So we'll take the derivative of y, treating u as the variable, so that is 3u squared. We'll find the derivative of u, treating w as the variable. That would be 1 over w. And we'll find the derivative of w, treating x as the variable, which would just be e to the x. Well, then dy dx is going to be the product of those, dy du times du dw times dw dx. Notice du and dw drop out. We get our dy dx out of it. So dy dx, 3u squared times 1 over w times e to the x. And then we just work backwards, get this written in terms of x's as our input variables. Okay, so u we have as natural log of 1 plus e to the x. So dy dx, hang on to that 3. And then we have natural log of 1 plus e to the x, quantity squared, times 1 over w, but w we said was 1 plus e to the x, times e to the x. So really not much cleanup to do. I would probably just multiply these monomials together and slap it over one denominator. So dy dx would be 3e to the x by natural log of 1 plus e to the x, quantity squared, over 1 plus e to the x. And that's as far as we need to take that one. So we might end up doing a couple subs in one problem. Okay, let's work through, well, this one's an interesting one. Y equals 5 plus e to the x cubed, quantity raised to the 4th, and we'll find the derivative there. So definitely this would be easier if y was just a u to the 4th, so that's what we'll do. We'll let y equal u to the 4th, which means we let u equal 5 plus e to the x cubed. And since this is not just e to cx, we'll do one more substitution. So we'll let w equal x cubed. So we have y is u to the 4th. U is 5 plus e to the now w power. And w is x cubed. Now we have three functions that are simpler to differentiate. Take them one piece at a time. So dy du, derivative of y, treating u as a variable. Power rule, 4u to the 3rd. Derivative of u, treating w as the variable. Derivative of a constant, that drops off. Derivative of e to the w is e to the w. And derivative of w with respect to the variable x, power rule again, 3x squared. So dy dx would be dy du times du dw times dw dx. So we have 4u cubed, e to the w, by 3x squared. We have a little bit that we can put together there. I can pull the 12x squared to the front of the line. u cubed, u is the same as 5 plus e to the x cubed, and that is quantity cubed. So I'll check them off as I'm using them. We use the 4 and the 3 to make the 12. The x squared's already there. Here is our u cubed. So then we just need e to the w. W is x cubed, so e to the x cubed. More likely the only other thing that would be done with that, that's another monomial. It'll likely be slid to the front of the line. So dy dx will likely be written as 12x squared e to the x cubed by 5 plus e to the x cubed quantity cubed. Okay, so we have you all try one out. Into that section of the book. We'll let y equal, we'll use one of your authors, modify one of your authors. 2 plus e to the opposite of x squared quantity raised to the 4th. So see if you can differentiate that. So go ahead and pause it, give it a spin, and unpause it when you're done. Okay, welcome back. So we'll start by making this y a u to the 4th, which means our u was 2 plus e to the opposite of x squared. Again, since this is not just e to the c times x, we'll do one more substitution. So w equal e to the opposite, or I'm sorry, just the top part of it, opposite of x squared. So then u is 2 plus e to the w. So you have y is u to the 4th. U is 2 plus e to the w, and w is opposite of x squared. So 3 pieces. So dy du, 4u cubed, du dw, e to the w, constant drops off, and dw dx, negative 2x to the 1st, or just negative 2x. So dy dx is the product of those 3. So 4u cubed e to the w by negative 2x. So dy dx be negative 8x. So I've used up this part, this part, this part. E to the w would be e to the opposite of x squared. And u cubed, u is a binomial, 2 plus e to the opposite of x squared, not strictly a binomial, since it's not a polynomial, but two-term expression. So there's our e to the w went there. There's our u cubed at the end of the line there. And really no more simplifying to do, so that is our derivative. All right, so in section 3.4, I would recommend 1 through 67 every other odd. So try 1, skip 3, try 5, skip 7, and so on. If you do need more practice, of course, you can try all the odds or even all of the problems in a section that you have trouble with. If you have any questions, please get in touch. Otherwise, I'll see you next time. Stay safe out there.